in my textbook. This is chapter 8. The material covered in this slide set is covered in your book. In fact, I should write. Where are we going to put it now? In brown, it's your chapter 8 plus the first 3 sections of chapter 9. So we're going to start off with some general concepts of bonding, what we think the chemical bond is like. First of all, what do we mean by a chemical bond? It seems intuitive, of course, based on the wording. Now we're talking about atoms that are held together as opposed to being separate. Another question that we'd like to answer is, why do atoms want to form compounds in the first place? I mean, wouldn't they be happier off by themselves? Oh, noble gases are. But most of the elements in the periodic table tend to form compounds of some kind, or at the very least, molecules with one of their neighbors of the same atom type. And then we want to eventually come up with some sort of a model that explains how these bonds are formed to make the compounds. Right? There's really no simple answer to the first question, what is a chemical bond? In fact, a chemist by the name of Linus Pauling wrote a whole book on it, Nature of the Chemical Bond. And his writings so impressed the world of chemists and physicists, for that matter, that he got a Nobel Prize for it. So in general, we can say a chemical bond is another way of saying the force that holds one atom to another or one group of atoms to another, and so that they function as a single unit. And this is a good general statement also. That's why I put it in bold and underlined it. In most cases, a bond will form if the aggregate energy of the products is lower than the aggregate energy of the reactants. It's kind of like you've heard the saying, the universe is running down. Most systems, when they start to develop, tend to gravitate, so to speak, to the lowest possible energy state they can attain. That increases stability. So this is what you might, this is probably a computer model that shows 2 separate hydrogen atoms, and they're sufficiently far apart that they don't interact. But when they come close together, the outer shells, where the electrons reside, interact. And then they form a bond, but the nuclei don't come right up next to each other. They sort of stand off. And that makes sense because their nuclei are positive. But they attain an optimum distance where the energy is the lowest possible for that arrangement of atoms. Now, a hydrogen atom doesn't have, these are not all electrons. These dots represent a scatter plot for possible locations of the electrons. Here's another way of representing it. If we go from right to left, we start from over here, we've got the separate atoms, and as they get closer and closer and closer, this is the distance between the nuclei, closer and closer, the energy starts to drop. Potential energy for the system starts to drop. And then if they get closer and closer, then the energy goes way up really fast. So this is their optimum distance right here with the lowest possible energy. That's when they're happiest as a molecule. If you push them together closer, and that's what happens in the sun, eventually you get them close enough together where the nuclei merge, and then you're not in chemistry anymore, you're in nuclear physics. Okay. We can divide bonding into two general categories. One, the easiest to understand, is ionic bonding. And that's where a positive ion and a negative ion, at least one of each, sometimes there are multiples, come in close enough proximity that their electrostatic attraction pulls them together. Right? A perfect example of that is sodium and chlorine. When they form ions, they tend to form chlorides, halogens form the negative ion, sodium forms the positive one ion. And this is the same for everybody in its group, the alkali metals. And same thing for everybody in halogen group. So all we have to do to write the compound is just balance the charges. But in order for this to happen, for instance, this type of reaction might occur. Sodium's a solid. Well, chlorine's actually diatomic. It's a gas. So when that happens, you get electrons transferred. Sodium is a metal. Metals like to give up their electrons. So sodium transfers electrons to chlorine, makes a chloride ion. And of course, to match that, we need two of them. And then you form two sodium chloride units. We really don't speak of these types of arrangements, the ionic bonding arrangements, as molecules. Molecules are bound together in such a way that they act independently. But the ionic compounds are in a matrix. And this is the simplest whole number ratio of one ion to the other. In fact, if you look at sodium and chlorine, chloride ion in their solid state, you see a crystal matrix with sodium ions surrounded by chloride ions. And similarly, each chloride is surrounded by sodium ions. So, where do you stop counting? If we look at just one, say sodium, you've got these four, plus you got one behind and one in front. So you've actually got 6 sodium. And then same thing for chloride. You've got sodium on 4 positions around and then one behind, one in front. So we actually have, that would be more accurate. Sodium 6, chloride 6. But we're going for the simplest whole number ratio. And that's why we have only one sodium, one chloride. That's known as a formula unit. Now, when we talk about covalent bonding, electrons are being shared. They're not completely transferred from one to the other. So when that happens, the bonding that forms here, the covalent bond, does produce molecules. And the perfect example of that is water. That oxygen shares electrons with this hydrogen and that hydrogen. And this molecule acts as a single unit. It doesn't come apart like sodium and chlorine do. There are intermediate cases. And truth be known, every compound possesses a certain amount of ionic and covalent character. So you can say, well, sodium chloride, it's mostly all ionic bond. And water molecule, it's mostly all covalent bond. But there's a gradient, and there's in-between space. Okay, when we have a bond, a covalent bond, now we'll focus on those. When you have a covalent bond, and the atoms are sharing electrons. To form that bond, they don't always share equally. Right? What's yours is yours. What's yours is mine, and what's mine is yours. But maybe the electron spends more time in my neighborhood because I have a stronger pull on electrons. Like I'm the grandparent and you're the parent, so your kids don't like you yet. They like me because I give them stuff. So that forms an uneven distribution of electron density. So when we go back to the water molecule, oxygen is more strongly attractive for electrons. So the electron density along this bond, or in that area actually, is more concentrated around the oxygen. And that tends to give this side of the bond a slightly negative charge. It's not a full negative charge, like a complete transfer of an electron, just a slight negative. That makes this one slight positive. So we use that little delta, the small Greek letter delta, to designate that difference. And then we use also this arrow with a plus on this end. This plus means that's the plus end. And that bond would be similar to it. Okay, that's a polar bond. What polar bonds do is they allow these molecules of water to interact with stronger forces between the molecules, because this negative side will line up with the positive sides on its neighbors, and there'll be a strong attraction. And you can see that evidence in the boiling point of water. Boiling point of water is 100 degrees Celsius. If it didn't have this characteristic, it would boil at less than room temperature, and the whole earth would be covered with maybe water vapor, but no liquid or no solids. So that's a good thing for us. Okay. You can measure the polarity of a bond, particularly if you have a diatomic molecule. Diatomic, two atoms, but they're different. They're different atoms, like hydrogen versus fluorine. When they're bound together, fluorine has a very strong attraction for electrons, but not so strong that it can turn this into an ionic compound. It's still covalent. And you can measure the current across these two plates with that fluorine gas in between, and do some calculations and some fine adjustments and determine the actual polarity of the bond, give it a number. Okay. I'm not going to rehash this, mostly because we don't have a lot of time. Okay, this is just in black and white what we've just discussed. I'll leave it up there long enough for the recording to catch it. Okay, this concept of uneven attraction of electrons has a name. It's called electronegativity. The stronger the attraction for electrons in a covalent bond, right? It's measured in a covalent bond. The stronger the attraction, the more electronegative the atom. And we do comparisons with them. We say, and there are several systems, right? There's not just one system that everybody agrees upon, but one that's very commonly used is Linus Pauling's system. And in his calculations and system for determining electronegativity, fluorine has the very strongest electronegativity in the whole periodic table. And cesium as the very lowest. So from lower left to upper right, we increase electronegativity in general. So this just describes Pauling's method for determining. This really isn't enough detail for us to go in and calculate those values, so I'm not going to spend any time on it. It just compares what we expect with what we see. Now, I will say, if you have two atoms of the same element, that's guaranteed to be a non-polar bond, such as, well, let's go back to oxygen. This would be the Lewis dot structure. We did that, didn't we? Lewis dot structures. Or is that what we're supposed to do today? Let's see. Maybe stealing my own thunder. I think we have done Lewis dot structures. No, it's coming. Sorry. So hold on to that thought. But if you've got the same atoms in the bond, then it's definitely nonpolar because nobody wins. They're both pulling the same string on the electrons. So that is a perfectly nonpolar bond. In fact, I would dare say that this has absolutely no ionic character whatsoever. It's only when you get different elements that you really start to see the polarity of the bond. Okay, and I just mentioned this. This electronegativity value generally increases across a period from left to right and decreases down a group. Now, there's a reason for that. As you go from left to right, you're in the same energy level, right? Same principal quantum number, N number. And as you go from left to right, you're adding electrons to that energy level. But what you're also doing is adding protons to the nucleus. So you're increasing the effective nuclear charge. And what that does is it causes more strong attraction for electrons. But as you're going down a group, you may be adding protons, but you're also adding electrons and at different energy levels as well. So the attraction for electrons outside the atom, which is what you're looking at when you form a bond, that attraction decreases because those inner layer electrons are shielding the outer ones, and any at infinity are shielding them from the added nuclear charge in the nucleus from the protons. So that's why go down a group, you decrease. So go up a group, you increase electronegativity. So that's why I said from lower left to upper right, you increase electronegativity. And in Pauling's system, it runs from 0.7 for cesium up to 4 for fluorine. Okay. And this is actually a pretty good representation of electronegativity in sort of a pseudo three-dimensional version. Now, each one of these elements has a number. And in this Pauling system, if you've got a bond formed between two of these elements, then you can subtract the lower one from the higher one and see what the difference is. And the higher the number, the more polar the bond. In fact, after you reach a certain point, you can consider that bond ionic. So if we say sodium is 0.9 and chlorine is 3, so that would be 2.1, right? And 2.1 difference in electronegativity. That would be an ionic bond. I think anything greater than 2. Or if we say 0.7 and 4, fluorine and cesium, that would be 3.3. That would be a very strong ionic bond. Okay, so which one has more attraction for electrons? Well, lithium's on the far left and fluorine's on the far right. It has to be fluorine. How about a bond between fluorine and iodine? Believe it or not, they will bond. Two halogens will bond. But when they do, fluorine has a stronger attraction than iodine because fluorine is further up. Yep. Okay. All right, we already said this. Lower left, upper right. There's the explanation. Across a period, increasing the number of protons and the effective nuclear charge. Whereas down a group, the electronegativity decreases because the size of the atom increases. And the electrons that are closer to the nucleus tend to shield the outside from the positive charge in the nucleus. Plus, it's just a bigger atom. And the electron density, the charge density is lower because it's spread over a bigger volume.
Yeah. So is electronegativity a part of why alkaline metals are so rapid to form?
Yeah. Yeah, I think that's fair to say. Yeah, and that's true. They are extremely reactive. In fact, I mean, if you want to crack your neighbor's swimming pool, just throw a big chunk of potassium in there and watch the fireworks. Because it'll get so hot, the reaction produces hydrogen gas. When it mixes with air, all you need is ignition source. And it's so exothermic that it'll set that thing on fire. That's why they keep alkaline metals, when you store them, they're in mineral oil, away from moisture in the air. Okay, so here's like the gradation between the two. The difference in electronegativity between the two atoms, if it's 0, it's definitely covalent, 100% covalent, if they're the same element. If there's more and more and more difference, you get more polarity, and at some point, we more or less arbitrarily decide that they're ionic in character, predominantly ionic. See, I thought I had those numbers somewhere. Are they in here? Maybe we discussed them in the problems in the review session. Yeah, that must be it. Because I don't see them in here. Where we draw the line, arbitrarily draw the line. Okay, let's move on. How about the following bonds from most to least polar? Okay, the closer they are together, the less ionic and more nonpolar they are. So let's see, nitrogen and fluorine, they're a couple of steps apart. Oxygen's even closer, carbon's farther away. So this one should be the most polar. This one would be the next polar, and that would be the most polar. That one, and that one, and that one. Okay. How about these? Since these are all bonded with fluorine, all we have to do is look at the relative positions of these atoms. But if we're looking at this one, right, we've got difference atoms. So we have to look at carbon and fluorine. Okay, they're 1, 2, 3 steps apart here. Nitrogen and oxygen, they're next door neighbors. They might be the least polar. Silicon and fluorine. Okay, so this is the least polar. And silicon's farther away than carbon is. So carbon and fluorine would be the next, and then silicon fluorine would be the most polar. Yeah, most to least. How about this one? That one's not even polar. I guess we could say it's least polar and be zero polarity. Boron and chlorine, they're pretty far apart. Sulfur and chlorine are right next door. Okay, so this is the most polar, this is the least polar, and that's in between. Okay, so that's sort of a qualitative assessment. Okay, which of the following bonds would be the least polar, yet still be considered polar covalent? So in order to answer that one, I work backwards. Still be considered polar covalent. So if there are any ionics in there, throw them out. Magnesium oxide is ionic. Right, so throw that one out. Silicon and oxygen, they're close enough to be covalent. But they're far enough apart that this is probably, well, we're looking for the least polar. All right, so that's the most polar. This one's not polar at all because they're the same atom, so we throw that one out too. So it's a race between carbon oxygen and nitrogen oxygen. So the least polar would be those that are closest together. Nitrogen and oxygen is closest together. That would be the least polar. Okay. Most polar without being considered ionic, I bet it's this one right here. They're the farthest apart on this periodic table. Yeah. And you can also check the numbers. You can say silicon and oxygen. Okay, silicon's 1.8, oxygen's 3.5, so that's what, 1.7. And then you can do the same thing with the others and compare the values. And the larger the value, the more polar it is. Yeah.
Do values apply with molecules too, or just base particles?
We're just talking about individual bonds right now. But when you get to where you're talking about more complex molecules, you take the polarity of the bonds into consideration, plus their geometry, how they're arranged in space. If you've got two equally polar bonds, like carbon dioxide, that's a linear molecule. So it may be polar this way and that way, but they're equal in strength and opposite direction, that's non-polar. Yeah, so it gets a little more complex when you start building molecules. And in fact, you can get molecules, once they get to a certain size, you can have the same molecule and one end will be polar and the other end will be non-polar. I mean, that's where soap comes from. That's why soap works, because most of the soiling, the dirtying of your clothes comes from oils in your skin, in the environment. They attract dirt. So the way to get them out, water doesn't do a very good job on its own because it's polar and oil's non-polar. But if you put soap in there, soap's got a non-polar end and then a polar end. It's the sodium, salt, and the fatty acid. So this is the polar end that attaches to water, and this is the non-polar end that dissolves in the oils, and it bridges the gap. So then it can be taken into solution and flushed down the toilet or down the drain. Nobody washes their clothes in the toilet, I don't think.
So anything below 2 is always going to be polar. Anything above it's going to be
Anything above it should be ionic. Non-polar, no. Covalent would be less than 2. And ionic would be greater than 2.
Yeah, but covalent is between non-polar and polar. I mean, like covalent makes non-polar and polar. Like that's what makes covalent.
Yes. So then you have another division below 2, where you decide, is it polar covalent or non-polar covalent? Yeah, I think the breaking point there is 1.2 or 3.
And everything, carbon, it's an ionic bond, just goes forever, ain't it? Like it bonds forever with itself.
No, as a covalent bond, yeah.
Because carbon anatomy teacher taught us that you just bonds forever. C equals C.
Well, yeah, actually carbon has lots of different forms. I mean, carbon itself, pure carbon, occurs in many different allotropes. It's graphite is one, diamond, pure carbon. We've got the fullerenes. You've heard buckyballs. There's 60 carbons covalently bonded in a nice big geodesic dome. And then you have nanotubes where they form a spiral tube. So it's very interesting. And you can, mono layers of graphite are being investigated as the base matrix for microelectronics because it has such interesting electronic properties as opposed to silicon. Everything, most commercial products now are silicon based because it's cheap, easy to make. Okay. Did I go too far? Yeah, there we go. So that arrow that I drew for the polarity of the bond, that indicates a dipole moment. And moment here is in physics terms. Moment means a direction and a force together. Let's see. Yeah, that's in words that describes this arrow. And this in words describes what I was saying. You need to know the individual bond polarities and then the geometry of the molecule. So if all the bonds in the molecule are nonpolar, you can't have a polar molecule. But just because they're polar doesn't mean it's a polar molecule. You need the right geometry too. So water has those two oxygen-hydrogen bonds, but it's bent. So when you vector add their polarities, oxygens here, then add them together, you get that. You know what I mean by vector addition? It takes into account not just the force, which is represented by the length of an arrow, but the direction. Or angular direction. Say if we have, in physics, we do it this way. If here's the point of contact, and you've got a pull in that direction, and the length of the arrow represents the force of the pull. But you've got another force that's pulling over here like this. Right? You want to know what's the combination? What does this actually feel? So the one way to do it, geometrically speaking, you can do it mathematically, but geometrically you can say, all right, we're going to draw a parallelogram. We're going to say this one is parallel to that one from this point, right? Equal to that length.
I would just think that there's some straight.
And this one is parallel to that one, equal in length. So that's our parallelogram. Now, the resultant, they call it, it's called the resultant of the two by vector addition is from here to there. So this, whatever is located at that point feels that direction and that magnitude of force. Like I said, you can do it mathematically too. You have your computer do all the calculating for you. Okay. So this is an artist's representation of the water molecule. It shows a dipole moment, vector addition in this direction. And then this is sort of an electron density representation. There's more electron density on this side of the molecule, less on this side. So the whole molecule is polar. But actually, when they start getting together, they don't just line up here with an oxygen there, and then an oxygen there, and an oxygen there. They actually go for the individual charge densities. So the oxygens of the neighbor is going to line up right here on that. And then its neighbor is going to line up on the hydrogen on that. So there's carbon dioxide, it's non-polar molecule, even though the bonds are polar. And especially when the molecules get really big and there's plenty of room, then you can get some interactions, even with a nonpolar molecule, you can get some interactions in here if you can fit the polars, the dipoles together from neighboring molecules. It's just, there may be steric hindrance that keeps them away. But the charge distribution is still there. Overall, it's nonpolar. And a good example of that is the, what's the boiling point of dinitrogen? Minus 195 Celsius. It's really, really cold. But a nonpolar molecule like carbon dioxide, I can't remember what its boiling point is. I know what its freezing point is, where you make dry ice. It's minus 78.5. Okay. So even though they're both nonpolar, there must be some attraction in here between these molecules, because this one makes a solid at that temperature. At that temperature, this one would still be a gas. So there's a difference there. Even though they're nonpolar, there is some difference in there to make that 117 degree or 116 degree difference. So we're talking in generalities. Okay. Let's see. Now, why is this one new here? Oh, example. Right. So for sulfur trioxide, you got polarity toward the oxygens, but they're all pointing in equal directions to an equilateral triangle, so they cancel each other out. And carbon tetrachloride is the same way. Chlorine is more electronegative than carbon, but it's a regular arrangement, so the vector addition is 0. That's why they used to use carbon tetrachloride to dry clean your clothes. It's very effective at dissolving oils. And it doesn't damage the fabrics. And when you've extracted all the oils from the clothes and your carbon tetrachloride, all you have to do is evaporate the carbon tetrachloride, and it leaves the oil behind. And then you just condense the CCl4 and reuse it. You purify it by distillation. Now, I don't know if most dry cleaners didn't have the facilities for that. So you would take the spent product and send it to a factory and they purify it again. But the OSHA and the EPA said, nah, can't use it anymore. It's too dangerous for your workers. So they had to find something else, a substitute that was obviously more expensive. Okay. So now we're trying to get at why atoms react with one another to form those bonds, why compounds form. As a general rule, an element will tend toward a noble gas electronic configuration. That's where it's headed. Mm-hmm. And for at least for the first 3, well, actually, the period 1 is a duet because it's hydrogen and helium. But period 2 and 3 are really good for this octet. They want that 8 outer. See, in period 2, we've done electronic configurations, haven't we? Or is that coming also? We're going to do that. How to write the electronic configuration of an atom. Well, let me write one and see if it rings a bell. Let's say Fluorine. Fluorine is nine protons, so it has 9 electrons. And its electronic configuration would be this.
That's what was on the list.
Okay,
I had to do that for 10. So.
I can't remember. Yeah, you're right, we did. Okay, 2, 4, and then 5 more. Okay, so fluorine, in order to satisfy its noble gas tendencies, it just needs 1 electron to make a full p orbital.
So it left makes it hydrogen.
Right. Right. So it either accepts an electron in an ionic bond, or it can form a covalent bond, and it has the feel of a noble gas. So this would be neon. It would look like neon if it were at a negative charge. And the octet they're referring to is the completed s and p orbital together. The valence electrons now are complete.
So all the other elements are those noble gases.
Yeah, that's the way. If we want to anthropomorphize it.
Well, they can be, I guess you could say. Well,
So you look at it in terms of which is more efficient, more energy efficient, to add an electron to look like a noble gas, or to lose an electron. And if you're on the non-metal side, it's usually easier to add electrons. That's why the halogens add 1, the chalcogens add 2 to jump over here, the pnictogens add 3, and then carbon can go either way.
Yeah.
But on the other side, it's easier for lithium just to lose an electron and look like helium, or beryllium to lose 2 electrons and look like helium. That's why the metals tend to be positive ions, and non-metals negative ions.
So is OG a noble gas too, or is that
Where are we? OG.
Open?
Oh, that one. Technically speaking, yeah, it's in that same family. Organoson.
Is it? 'Cause that's what-
Organoson. Yeah. Tennessine would be the halogen.
I never heard of those really in high school.
No, they're recent. They used to just have placeholders in here instead of these names. Like my favorite is this one, now called Rentenium 111. That was ununium.
Yeah, I remember that. And then I don't remember RN that good either.
Radon.
Yeah, I remember it being there, but we didn't use it much.
Yeah, radon is a noble gas, but it's radioactive.
Yeah, because I remember being. I don't remember those either. Though.
I think-
thought sticky notes.
Isn't that one the Curies identified?
I think so.
Yeah.
And LU and LR, they're on their own. They ain't noble gas, right?
Oh, no. This is purely a coincidence that it's down here, because all these are supposed to fit right in that crack.
Okay.
Right? Those are the lanthanides.
So you wouldn't be happy if they found a new element with you.
Wow, we'd have to redo the whole table.
I know that's what my high school teacher said. He said I hate it.
Yeah. Yeah. We'd either have to shrink that one to fit the same size, or we'd have to balloon the chart to take it in.
What would it be though? Would it even be a middle if they found it up? Because it'd have to take the atom out of. Oh.
It would be difficult. It would be difficult to characterize because all of these are radioactive. Very, very limited lives. Yeah. You can't gather enough of it together to do traditional analyses.
Because he said they put an atom of the highest, like OG, they'd have to put that, and they put an atom right there, and they send whatever it was straight to the atom and make the element. That's how they did it or something.
Oh, yeah. Yeah, you put them in a particle accelerator.
Yeah, now you make me think of the flash.
Yeah. But the Schrodinger wave equations are capable of predicting electron structures for higher elements.
Do you think they'll try to make an element, or do you think they just?
Oh, sure. Yeah. If it can if there's any chance at all that it could be done, somebody's going to try it.
Probably not gonna be good.
That's human nature.
One of these days, they're probably not gonna be too happy with the new one that they create.
And they've already got names for them. They can pick from any of the science fiction movies.
Yeah, they got a lot of names for that.
Yeah. New elements and new forms of energy. What's that one? Theta radiation. That's supposed to be deadly.
And then there's a metal, what's that metal called from Wakanda or something? In the Marvel movies. Black Panther.
The one that,
Starts with a V. I can't remember the name.
what's the one they injected into Wolverine?
One that just titanium, no,
No, it was adamantium.
yeah.
Yeah.
It is.
So
Yeah.
at some point, the charge and size of the nucleus of the atom just kind of counteracts the strong nuclear force that pulls it together.
Yeah. Yeah, they, and as the nucleus gets bigger and bigger and bigger, it takes more and more neutrons to hold it together. And there's probably a limit to how many positive charges you can cram together and still make them stable enough. Well, in fact, by the time you get to these, they're all unstable, very unstable.
That's like 83 gallons.
I'm sorry.
Isn't it like 83 gallons? That's
Yeah, I believe you're right. Yeah, polonium and up should be radioactive. And then there's one in here right there, technetium. That is radioactive. Yeah, but the rest are heavy elements.
Where do I find the video on Blackboard?
The video,
For example,
oh, for this, it's a link. You want to pull it up, show me?
you don't have to, you can explain it. Is it on Blackboard?
Yeah, you just go into the, I think I've got it subdivided into exams, and then inside the exams, there are levels for PowerPoints. But they are probably separate folders. A folder for the PowerPoints, a folder for the review documents, and then interspersed in there, you'll see occasionally it will appear a link to a video.
Okay, so this would be underneath like Exam6 then probably.
Yeah. And you just click on that link and it takes you to YouTube. I store all my videos on YouTube and just put a link in
I've watched one of your videos where I got to it.
there. Or you can subscribe to my channel.
I think I did, honestly. I probably did.
It's,
I usually do that whenever it's a feature.
I really don't care. I'm not monetized, so it doesn't matter to me.
Yeah, I know, but I'll put it on there, sign up, and always go back to the videos.
Okay. Yeah, I mean, I lost count. I don't know how, several hundred now. I've been doing this for a few years. And you can tell the earlier ones are really poor quality.
Hey, the more subscribers you have, the more money you like.
Yeah, I'm probably running some legal problems because I'm already being paid to make these things. Right? So if I try to make money off of YouTube doing them, there'll be some legal repercussions, I bet.
I don't know, because there are people like, there are teachers that do it, and I think they get money from it too, so I don't think, as long as you prepare for the problem.
Okay, I have been cited for a copyright violation once. I was using, I started my videos off with the lead into television show, The Twilight Zone, the old version, right, where you have an eyeball and door coming at you. And they said, you can't do that.
Some people do that. I guess they.
They probably buy copyright for it.
That's what I'm saying. They probably have to pay for it.
I thought that as an educational exercise that I could get away with it, but no. Okay. There are exceptions to this octet rule in the configurations, but they usually occur in the periods 4 and higher, right here. When you get to this one, Now, once you work across there, you're getting into d orbitals. And that messes with your octet rule. So when you get over here, say 10 could form 2+ and could form 4+. Lead 2+, 4, bismuth 3 and 5. Those are possible ions. And they're all related to the energy interactions with those different orbitals, the P's, the D's, and the S's. Oh, forgot thallium. Okay. The sharing of electrons gives the individual atoms the feel as if they are noble gases, whereas you don't actually transfer electrons to them. They tend to count them as theirs. And they may be for a short time, those are my electrons, and now you can have them for a while. It's kind of like a divorce, sharing the kids. Let's see. Okay, when you do get the non-metal and the metal-non-metal interactions, when the metal is a representative group element, most often up in this area or this area, then they tend to actually achieve noble gas configurations in their electronic structure. Isoelectronic series. We've learned how to write the electronic structure for atoms and some ions. And all you have to do is just write out the neutral version. And then if it's a positive ion, you just take one electron away and see what that does to the structure. If it's negative, then you just add an electron and see what that does. But all of these are in an isoelectronic series because they have identical electronic configurations. The 1s, 2s, 2p, and all the way across, exactly the same. And since neon is in this group and we're saying it's part of the series, they all look like neon. It doesn't have to be that way. In other words, you can form isoelectronic series without a noble gas in there. And all they have to meet the conditions is the same electronic structure. Okay. All right, we don't have time to do this. Just one example. Actually, it's easy to do it. If you've got a noble gas in there that you're saying they're all equal to, all you have to do is say what group is it, form the ion, and it's equal to the noble gas. Right? So chlorine ion would be argon. Sulfur ion would be argon. Phosphorus ion would be argon. Or potassium ion would be argon. Calcium ion would be argon. It looked like argon.
So if you had only the electron configuration and like you didn't know what it was, you could put any of those as an answer, really.
If you have the electronic configuration for an element or an ion, well, if it's neutral, if you're told that it's neutral, then you can identify which element it is.
Yeah, but if it don't specify, then you can put any of them in there, right?
Oh yeah, it could be any one of those ions.
If it said like
Yeah.
neutral, it'd have to be argon. But if it said like -1 or something, it'd be like
Oh, if it said -1, it would have to be that one.
chlorine or plus. If
Yeah,
potassium
right.
plus two, it'd be.
Yeah.
You can make someone mad by doing that.
Yeah, the number of electrons are exactly equal for each one of those. but then the protons are different based upon the charge. So if they all have the same number of electrons, then if you have one proton more, that's a positive +1 ion. If you have you have two more protons, it's a +2. Or if you have 17 protons, it's a -1. Yeah. Okay, we've talked about these already. Atomic size, ionic radius we haven't talked about. We've looked at ionization energy and electronegativity as a trend in the periodic table. We know how to do electron configurations. We know how to predict the formulas for ionic compounds. And we know covalent bond polarities and how to rank those. The one we haven't talked about very much is ionic radius. As a general rule, if you form a negative ion from a neutral atom, you increase its radius. You got an extra electron out there taking up space. Or if you take one away, it shrinks it. So that's why when you see representations of sodium chloride, you see the sodiums are like this, and the chlorides are like that. Besides, the chloride, if you have neutral atoms, the trend is going to be they shrink going from left to right. Right? The radius decreases that direction. Right? It decreases from lower left to upper right. So from left to right, the radius decreases because you're adding more protons, and they're not shielded. But when you add that extra electron out there, then it balloons way out. Whereas the sodium, you subtract an electron and it shrinks.
Do you mind if I leave?
If you have to, sure. Yeah, I'll finish the discussion.
That's why I was asking if you put it on
I
board to make sure, because I keep getting phone.
never make the connection.
I know, I was really sorry, I didn't want to.
Okay, so let's see where we're headed next. What are the factors that influence the stability and the structure of solid binary ion compounds? All right. Well, one thing, how strongly do the ions attract one another? And there are factors that affect that. And we can quantify the amount of energy that's responsible for the bonding, and we call it lattice energy. There's a definition for that, and I'll get to it in a second. When you have two separated gaseous ions, right, here we are again. Remember when we did ionization energy, we had to start from a gas so that we didn't have phase change influences the energy calculations. So in this lattice energy, we're actually going from, let's say we have one cation here, that's a gas, and we have an anion here, that's also a gas. Let's just say it's simple diatomic like that. When it forms a solid from those two, then there's energy given off. It's an exothermic process. That is the lattice energy. And since it's energy leaving the system, it'll always have a negative value, a negative sign. This theoretically, we should be able to calculate the lattice energy. This is the way you do it practically, right? In the laboratory, you would take these gases, put them together, and measure the output of energy. But you should be able to calculate the lattice energy based upon the charge on the ions, right? So it doesn't have to be just +1 or -1. It can be multiple charges. So this indicates the strength of attraction between, you would expect this and this to have a much stronger attraction than that and that because of the number of charges. Okay. That's one factor. The other factor is how close can they get together? If they move really close together, then the strength of attraction is stronger. It's kind of like the Newton's law of universal gravitation. The closer the bodies are together, the stronger the gravity is, and the bigger they are, the stronger the gravity is. So it's that similar concept. And then you have a proportionality constant that takes into account the units, because this is going to be in joules, and this charge is going to be in probably coulombs, and the distance is going to be in who knows what. Well, standard measure would be meters. So you need a proportionality constant to make these things jive. Okay. So that's lattice energy, but that's not the way the reaction occurs between a metal and a non-metal. So when you get a metal and a non-metal together, then certain things have to happen. Most metals are solids. So first of all, you have to change the solid to a gas. And we're going in steps here because this is the way we logically approach it. In reality, like I said, nature just does what it does. You put those two together, all this stuff happens. But we're thinking about it in stepwise form so that we can make sense of what's happening. Okay, so we make a gas out of the metal first, then we make an ion, and that requires energy, endothermic, endothermic. So we go from here, the solid, down to the gas ion. And this example is just a +1 charge. If you need to make a +2 charge to make the compound, then you would have another step in here with more energy input. Then you take the non-metal. Now we've got the ion ready. Now you take the non-metal, and in this case, the non-metal is a diatomic, which is true for some of them. And we split that apart so that we make one of these gaseous non-metal atoms. And then we take that atom and ionize it. So that's, actually, we don't ionize it. We invoke electron affinity. So that's an exothermic process. Let's simply back up. Endothermic to make this, yes, that's true. Break that bond, put energy in. And then we get some energy back when we add an electron to it. And then we take, now that we've got the gaseous anion and the gaseous cation, we put them together. And that's exothermic. Actually, very exothermic usually. And then to determine the enthalpy of that whole reaction, formation of that compound, you have to add all those terms together and see which one's bigger. I mean, is it an exothermic or an endothermic process? It just depends on the size of the steps. All right, so here it is in miniaturized form, which you probably won't be able to see on video. But there should be something similar to this in your textbook too. Most of them do have something like that, stepwise. Okay, so here we have an example of making lithium fluoride. So here's actually, this is the formation reaction, where we find the energy of formation, enthalpy of formation. I remember when we wrote those, you start with the compound, you write the compound, and then you work your way back over here, and you have to go elements in their most stable state. So that's lithium solid, difluorine gas. And then you use whatever coefficients you need to make this 1 mole. Okay. And that has an enthalpy of formation for that compound. Well, we can bust it apart and say, all right, first we're going to take the lithium, make a gas out of it, which requires input, that's misleading. That shouldn't be there because that makes you think it's a negative, but it's not. You have to put energy in to get there. Let me make a note. Find these things wrong with my slides. So that's misleading. Okay, so this. Is that not the same? That's not the same. Oh, they're out of order. They're out of order too here. Oh, okay. It needs a lot of work. Just put it that way. So we put this much energy in to get there. Then we take that and we put some more energy in to make the ion. Okay. Now we take the difluorine, and how much energy does it take to make this? Well, if it's based upon 154 kilojoules input to get that, but we only need half of it. So we really only need 77 kilojoules to give us half a molecule. And then we have the electron affinity. Now we are going to get some energy back with this one. So that is true, that's negative. And then we say lithium gas and fluorine gas make solid lithium fluoride. And the energy involved for that, the lattice energy, is negative 1,000. So we put all these together, and the enthalpy of formation is this one. Overall change is minus 617 kilojoules for that equation, I think. And that's where we add these steps together. Now, the reason we can do that is the same reason that Hess's law works, because this is a state function. Enthalpy is a state. So it doesn't matter how you get there. You can take as many steps as you need, just add them all together, and you end up at that same location. Okay, well, there it is in a table form anyway. Partial ionic character. In order to determine the percent ionic character of a bond, we measure the dipole and then we compare it to the calculated dipole. The measured dipole moment of the covalent bond. Then we compare it with the calculated dipole of the ionic bond. And that's probably, they use that equation we just saw a minute ago. And just ratio them, and that tells you the percent ionic character. And this is a scatter plot for some compounds. Right? HF, and these are all supposed to be covalent. Oh, there's a good, yeah, electronegativity. So anything less than 2 here. Well, now that says that these, well, it's like I said, they have ionic character and covalent character. Electronegativity differences. So this one is greater than 1/2. These are greater than 1/2. But greater than 2, these are definitely ionic here, but predominantly diionic. And these are kind of bridge the gap. More definitions. An ionic compound will only conduct electricity if the ions are free to move. And you can do that in several ways, actually. You can take a solid and melt it, just add enough heat and separate the ions in the melt. Like you can use heat and make table salt into a liquid. You have to get it really hot. And there are some systems that use liquid sodium chloride as a heat transfer medium. Very efficient. Or if it's soluble in water, say, you just put it in water and water will do the work for you. It'll break that thing apart into individual ions and now you can conduct electricity with it. But you got to have mobile ions in order to transfer current. from one electrode to another. Okay, now we're going to look at some models. And models imply a theory. That is, we're attempting to say why things happen the way they do. Okay. Well, these are fundamental properties of a model. I've mentioned models before without really giving much detail. The first thing to remember is that a model is not reality. It's like a model airplane, right? Is that model a real airplane? No, it just looks like one. And it's got as many pieces in it as you need to make it act as an airplane or look like, or whatever the case may be. But it's not the real thing. They're most often oversimplifications. And for that reason, they're usually wrong. They have to be modified or scrapped or restricted in use. If we tend to modify them, then they always become more complex. And the complexity is okay for a while because it adds the ability to predict using the model. But at some point, if you keep modifying the model, eventually you modify it beyond its usefulness. And never forget that it's not reality. So we have to understand any underlying assumptions that are made in the creation of the model. Like let's see, if we talked about the kinetic molecular theory of gases, I think we had. And there's some assumptions that are made when that model is proposed that are relative to ideal gases. So whenever you deviate from ideal behavior, then the model's not as effective in explaining what's happening. But all is not lost. If we discover that the model is wrong, I mean, just fundamentally in error, it can teach us something about the system that we're studying. We may have to generate a new model, but we know, like Albert Einstein, not Albert Einstein, Edison, Thomas Edison said, or a reporter asked him, says, I understand that you failed 99 times when you were trying to make a light bulb. And he says, no, I didn't fail. I just found 99 ways that you can't make a light bulb. So he learned something from the failures and eventually came up with one that worked, or at least his team did. So this is what you do when the model stops working. Sometimes you just say, we're going to restrict its application, right? We know its boundaries now. If you want to investigate something out here, don't use our model. And many of them are like that. Newton's laws of motion are like that. I mean, this is not chemistry, but it's an example. You can only use Newton's laws of motion in classical situations, and we define what classical is. Right? It's not too small, it's not too big, it's just right. Or you can continue to modify the model to accommodate new conditions. It's easier if you're doing this mathematically to make those modifications than it is if you have a physical model. And it can get really ridiculous. Like, we normally think of space as occupied, matter part of space is 3 dimensions, defines the volume. But we can add one more dimension, time. But there's some theoretical physicists that just go wild with their math, like 26 dimensions to accommodate their theory. That's a little extreme, I think. Or you can throw it out and start over. And sometimes we have to do Oh, here's an example. J.J. Thomson plum pudding model of the atom. Once Rutherford proved him wrong, they just had to throw that model out. There's no modifying that one. It was just pure D wrong. Okay, what's a bond energy? Well, it's the energy required to break a bond, or it's the energy you get back when the bond forms. If you're breaking the bond, of course, it's endothermic, and the energy carries a positive charge. Or if you form the bond, energy is released, and the value is negative. You can have single bonds, double bonds, triple bonds. So let's see, example, hydrogen. Is bonded with one electron from one hydrogen, one electron from the other, forms a bond. Oxygen, 2 electrons from this oxygen, 2 from that one, makes a double bond. Anytime you have 2 electrons in a bond, it's a line. So sometimes instead of writing it that way, we just put a line. That's 2 electrons, that's 2 electrons. This would be 2 electrons. Or nitrogen is 3 electrons. That's a triple bond. As a general rule, the length of the bond shortens as you multiply the bonds. So this one would be shorter distance than that one, and this one would be shorter distance than that one. It's not a linear change. Right? This one's not twice as short as that. And I'll eventually show you why that is when we start talking about models for bonding. But it is shorter, and it contains takes more energy to break this bond than it does to break this one than it does to break that one. And here's the evidence, right? The bond energy for this hydrogen is 432, but this one is a stronger bond, HF. It takes more energy. This one's about the same. HBr is less, HI is less. And all these bonds can be quantified. Okay, so we are. We've already talked about that. Endothermic versus exothermic. Okay. You can use bond energies to calculate the enthalpy of a reaction. And it's very accurate. So if we know a reaction takes place, say, let's use a simple example. Say methane gas and oxygen gas yields carbon dioxide gas and water liquid under standard conditions, standard temperature and pressure. We just need to balance it. So let's see, carbon, 4 hydrogens, 4 hydrogens. See, that means 2 oxygens, 2 oxygens, 4 oxygens. So that should be balanced. Yeah, that's balanced. Okay, suppose we want to know what the enthalpy of that reaction is. Well, I can tell you it's going to be exothermic. But if we look at the individual bonds that are part of this, we've got this one for methane. Oxygen is a double bond here. Carbon dioxide is COO, and water is this one. There are 2 of these, 1 of these, 2 of these, and 1 of those. So what you can do is, this formula tells you that you take the energy required to break the bonds broken, so that's this group right here, and then you subtract the energy of the bonds that are formed, this group over here. So we look at that chart. Here we go. Right, carbon, hydrogen. Where's that one? Carbon, hydrogen, 413. Is that joules or kilojoules? Probably kilojoules per mole. So we got 4 of them. Right, add up those 4. And then we got 2 these oxygen-oxygen bonds here, 495. 2 times that, add those together. And then we subtract the energy of these bonds. So we've got 2 carbon-oxygen bonds, right? Yeah, carbon. Let's see. Yes, 745 times 2. And then we got 2 oxygen hydrogens, but 2 times that is 4. So 4 times oxygen hydrogens here, 467. And add those together here, add these together and subtract those from this one, and you get a value for that reaction of delta H. I think I got an example. Here we go. This is a really simple one. Right? If you look too quick, they look like, what's the difference? Right? They look the same. Well, they have the same atoms, but they're arranged differently. Right? On this side, you've got this nitrogen bound to that carbon, and then the 3 hydrogens positioned around it. And then the triple bond over here with the carbon. On this one, you've got a carbon-carbon bond instead of a carbon-nitrogen bond, and the 3 hydrogens around it. And the triple carbon-nitrogen triple bond. So these are both the same on both sides. The carbon hydrogens are the same. The only difference is this carbon-carbon and that carbon-nitrogen. So if we take this carbon-nitrogen and subtract the carbon-carbon, we should get 42. The difference between these two is 42 kilojoules, or negative 42. Okay, now for the models. Trying to understand something about the bonding and the shapes of molecules. This localized electron model says that in a molecule, atoms that are bound together and share electrons are actually using the atomic orbitals of individual elements. And then they overlap in order to form the bond. So that's why it says localized. We're still trying to use the bonds from the energy levels, the orbitals. Use the orbitals from each atom to overlap and share electrons. So the electrons themselves still consider home, right? If you got oxygen and hydrogen, the electrons in here still consider this one belongs here and this one belongs here, but they sort of share in the middle, and they overlap orbitals in order to make that bond. So that's the localized electron bond. And the bond itself is formed from these electron pairs. So in order to form one bond, you have 2 electrons in between the atoms forming the bond. Unless they're not part of the bond. Sometimes you have electrons that are not part of the bonding, and they are the lone pairs or non-bonding pairs versus the bonding pairs. These are the ones that are between the atoms and forming the bond. These are lone pairs. For instance, oxygen. When oxygen bonds with another oxygen atom, it has 2 lone pairs each. And we know that that works because if you say this is 2, 4, 6, 8, there's an octet. 2, 4, 6, 8, there's an octet. That's what we're headed for with this model. trying to form the octet. So that by definition is what they are and where they're located. Now, what we're going to do first, at least for this exam in Chapter 8 and 9.1 to 9.3, we're going to look at these first two, Part 1. We're going to have to, first step is to learn how to draw Lewis structures. And they're based upon the Octet Rule. And then we're going to take that information and use this, actually models can have submodels. The localized electron model has this BSEPR model, and I'll explain what that is in a minute. And that helps us predict the geometry of the molecules. Then part 3, we're going to pick up in a separate exam. The rest of chapter 9 will cover this material. So you don't have to worry about that right now. We're going to focus on part 1 and part 2. So how do we draw a Lewis structure? Well, G.N. Lewis was a world-renowned chemist. And he wanted a simple way to approach bonding of atoms. And he assumed that when you formed a bond, a single bond, you have 2 electrons. So if we were able to use the symbols on the periodic table, and then around them only put the valence electrons, those that were involved in the reaction itself. And the rest of them you could just ignore because they're not involved. And he assumed that the reaction tended to make a complete octet. Okay, so if he drew the electronic structure with only the valence electrons around the symbol, then he could say, all right, if this one's only got 5 around it, then it needs 3 more to make an octet. So where does he get those 3? Well, it could come from 3 fluorines, or it could come from 3 hydrogens, or whatever the case may be. It'll become obvious once we start drawing. Okay, so I said the octet rule, but hydrogen is a special case. Hydrogen only has a 1s orbital, right? So it's only got 1 electron by itself, but if it can get another electron from some other place, it can change that to a 2, and now it looks like helium. So hydrogen obeys the duet rule, and everybody else obeys the octet rule. Okay, so let's see. Here we go. How to write a Lewis dot structure. Here it is in words, and I think we ought to just go draw one. And it uses these rules, so you can go back to them if you want. Oh, I wouldn't emphasize this. When you're given a molecular formula, sometimes it's hard to tell which atom goes here and which atom goes out here, like this, which one's in the center, and which one forms the bond. Usually the more electronegative one goes in the center. And the more electronegative one is to the right and above, if you've got 2 that you have to decide against. Most of the time. There are some exceptions, and you just have to memorize those. Okay, so here's what we do first. For water, you just take all the valence electrons and add them up. Right, so we have a hydrogen with 1 valence electron, but we got 2 of them. So there are 2 valence electrons. Oxygen has 6 valence electrons, right? Because it's got a 1s, and it has a 2s and a 2p. And the valence electrons are the 2s and the 2p. And they have 6 electrons between them. So you add those together, and you have 8 valence electrons that you can use in the Lewis dot structure. Okay. So next, you put the more electronegative one in the center, and you form a single bond with the other atoms. So now we've used up 4 electrons from our 8. That means we've got 4 more to a position. So what do you do with those 4? Let's see, did I skip something? No, I guess not. Okay. Then you start writing. So we've done this so far. 2, 4 electrons, we've got 4 more. You start from the outside and work your way in. Hydrogen can't take anymore. It's already got us do that. So the rest of those electrons have to go on the central atom. 4 electrons. So you say 1, 2, 3, 4. There you go. So you can count them up, 2, 4, 6, 8. We've used up all our valence electrons. That's the Lewis dot structure for water. Now, that's not the geometric shape. We haven't got there yet. That's what we call a valid Lewis dot structure. And there are some molecules or complex ions, actually, not complex ions, polyatomic ions, can have more than one valid Lewis dot structure. And that's one of the Achilles heel of the method. So let's see, which one do we want to do? Well, there's water. If we do the same thing with phosphorus tribromide, phosphorus has how many? Well, let's see, let's look up here. If you want to find how many valence electrons, you just count from the left. 1, 2, 3, 4, 5. So phosphorus has 5 valence electrons. Bromine, keep going, 5, 6, 7. 5, 6, 7. Bromine has 7 valence electrons. So 3 times 7 is 21 plus 5 is 26. 26 valence electrons. And then you position phosphorus in the middle. So here's where we have to sort of deviate. Because which one's more electronegative? Well, maybe phosphorus. I really don't know unless I look at the chart. But I know to put phosphorus in the middle and make a single bond with bromine. So there's 2, 4, 6 used up. Then we go around and say, okay, start putting electrons around here until we get an octet. And once you got an octet on the outside, the leftovers have to go on the central atom. So that being said, now we have 2, 4, 6, 8, 2, 4, 6, 8 for all the bromines. Everybody's got an octet, they're happy. You can do the same thing. You can do the same thing for hydrogen cyanide. Let's do that one before we put it up there. So hydrogen cyanide. Let's see, there's 1 here. There's 4 for carbon, and there are 5 for nitrogen. So that's 10 valence electrons. Okay. Carbon's going to be in the middle. So we do 1 with nitrogen, 1 with hydrogen. Okay. Hydrogen's satisfied. We can't put any more there. So we got 2, 4, 6 electrons left. 1, 2, 3, 4, 5, 6. Okay. Now we've used up all our electrons, but nitrogen has an octet, carbon doesn't. So how do we fix that? Well, we make carbon feel like it's got 8 electrons. We take these 2, make another bond. Take these 2, make another bond. So now we have like that. Let's see, 2, 4, 6, 8, 10. That way, carbon feels like it has an octet. Nitrogen still has its octet. Hydrogen has its duet. That's a valid Lewis dot structure. Okay. I'm running short of time. Let's see. Oh man, I've got too many slides to go. I'm going to have to blast through these somehow. Okay. We know that the structure of oxygen, water, is bent like this. How do we get from here to here? You can draw those on your own. Draw those on your own. They're pretty tame. They behave. We'll come back to that geometry because we need a little bit more information. But just remember, there are some molecules that do not obey. That's another Achilles heel for the Lewis dot structure. We know this compound exists, boron trihydride. It's real. But if we draw the Lewis dot structure, there are 3 electrons for boron and 3 for the hydrogen, so that's 6. And if we put a bond each here, we've used them all up, and boron doesn't have an octet. But it exists. So this is a deviation from the Lewis dot structure rules. It doesn't have an octet. We can go the other way too. We can form sulfur tetrafluoride, which has 34 electrons. And if we put all the octets around fluorine here that we have, we're going to have 2 electrons left over. So they have to go on the central atom. Now sulfur has 10 instead of an octet. It has 2, 4, 6, 8, 10. Similarly for arsenic. It has 10, but they're all in bonds. Okay, so why can that happen? Well, we look at where they're located. Sulfur's right here, and arsenic's right there. So at the 3rd principal quantum number, what do we have available to us? 0, 1, and 2. S, P, and D. D orbitals are available to sulfur, and D orbitals are available to arsenic. That's where those extra electrons are going. Right? So the octet doesn't work there because we have D orbitals available. Okay, so we can draw these. Now, the Lewis dot structure for this one could be that way, or we could put a double bond here, we could put a double bond there. Those are all 3 valid Lewis dot structures. And we'll have to talk about the solution to that later. Here we've got exceeding the octet for phosphorus. Exceeding the octet for sulfur. By quite a bit, actually, the 12 electrons around sulfur. Okay, these are review statements, and makes a point here of the d orbitals being available, allows us to exceed the octet. Okay, let's see. So when we have more than one valid Lewis dot structure, we invoke a modification to the theory called resonance. So we say, okay, since we're a localized electron model, we have to treat these electrons as if they belong to one of the atoms, and they're just shared by overlapping orbitals. So if this one's valid, and that one's valid, and that one's valid, we just say, all right, they're all 3 valid, so there's resonance among these 3. They just move back and forth so fast we can't tell. Now, we know that this standing alone is not a valid structure because we've been able to measure the length of these bonds. And in addition to the energy of this bond being greater than that bond, if this were true, that bond should also be shorter because the bond is stronger. But it's not. All of these bonds are equivalent. Okay. Another way to write that is put nitrogen here, like that, that. I'm going to leave off the lone pairs. Have a charge. And sometimes we do like this. Partial double bonds. The problem with that is, if you want to do any reactions with it, there's no way to deal with those. It's got to be whole, single, double, or triple, or it doesn't work. But for standalone, that gives you an idea of the fact that each one of those bonds is equal in strength and length. Right? So this is a fix, a modification that is not the best, but a useful fix sometimes. Okay. So we're not going to take time to draw those. We're going to introduce a concept called formal charge. We've looked at so far a bookkeeping scheme for electrons, I think. Have we not? Oxidation states, have we done those? Yeah, oxidation states. Oxidation states are okay. You know, if you're gonna do some electrochemical type reactions. But in covalent bonding, particularly in organic chemicals, it's more useful to invoke a different method called formal charge. And basically what it is we look at the number of valence electrons on the free atom. So carbon would have 4, nitrogen would have 5 valence electrons. Then we look at the number of electrons that surround the atom when it's bonded. And we subtract those electrons around the bonded atom with the electrons around the free atom. And that's the formal charge. Right? So if carbon were in a molecule where it had 4 electrons as a free atom, and now it only has 3 electrons in the bonding, then its formal charge is +1. Okay, and the value of that is we look at those Lewis dot structures, and if you have competing structures that you've been able to draw, you want to see which one's the best, or do I have to keep all of them? If you look at the formal charge on all of the elements in that molecule, as it's written Lewis dot structures style, then you look at the formal charges and you say the ones that have the lowest overall formal charge is the most stable, and that's the one we go with. Oh. Okay. So how do you count them? Well, if we have, let's see, carbon dioxide. It's going to have a structure like this, this, and this. So there's your octet, 2468, 2468, there. So carbon has 4, and now you count bonds as half electrons go to one and half electrons go to the other. So this electron goes that way and this one goes that way. So this one has 1, 2, 3, 4. 4 electrons in the bond with 4 electrons in its free state. It has a formal charge of 0. This one has, let's see, oxygen would have 6 valence electrons, right? So which side did I put them on? This is free atom, right? So the bonded one has 1, 2, 3, 4, 5, 6. And the free one has 6. So all of these have formal charge of 0. And that's the best, actually, that's the only Lewis dot structure I can think of for that. I guess I could draw a weird one, like put triple bond on one side and single on the other. But we count lone pairs as belonging to that atom, and we count bonding pairs as split half one way and one the other way when you're counting up electrons in the bonds to compare with the free atom electrons. Okay. So this one gives phosphorus a +1 formal charge. Oxygen is a -1 formal charge. And chlorine is 0. Just as an example. Okay. Oh, good. They did it for me. So if we're saying this is 2468, 2468, 2468, that's a valid Lewis dot structure. So is this one. So which one's valid? Well, this one's all zeros. And this one would be oxygen has 6, and now it has 2467. So it's got a -1, and this one's probably a +1, and this one will still be a 0. So this one's better because they're all zeros and they're not negative, positive. Okay, we always have to remember, just like with oxidation states, we're not actually saying that there's a charge. We're just saying this is a bookkeeping scheme for our electrons. So we're not saying, and especially if they're covalent compounds, right? And most of the ones that we do, Lewis dot structures, are covalents. So we have to recognize that that's not a real charge. It's just a method. Okay, now here's what you do with the Lewis dot structure. We use the VSEPR model, which stands for valence shell electron pair repulsion. No, that's a mouthful. But these valence shell electrons are located either as lone pairs or in bonds. And you count up the numbers of groups in the bond. I'll get to that in a second. Let me finish this one. And they say electron pairs, I say electron groups. But I inherited this, so I have to keep that part. And we're looking at the repulsion. So these electrons in the bonds and the lone pairs are repelling one another. And the lowest possible energy state is the one in which they are spread as far apart from each other as possible. Right? And you do that with usually regular geometric structures. You minimize the repulsions. That's the whole point of this model. Right? So if we have something like this, let's see. Carbon dioxide. It's a valid Lewis dot structure. That's our preferred structure. Then when we talk about the geometry, we always talk about the geometry based on a central atom. So if it's a complex molecule, you would say the geometry about this atom, the geometry about that atom, geometry about that atom. They have separate geometries. But with these simple models, we can go with just that atom. So now this one has two electron groups around the central atom. Whenever that happens, the structure is always linear. Okay? Now, I might as well introduce it here. This linearity is referencing the electron groups. All right, there's one group, there's another group. If we had something with lone pairs around it, like water, has a lone pair here and a lone pair there. How many groups do we have here? 1, 2, 3, 4. 4 groups of electrons, whether they're lone paired or bonding, means we have a tetrahedron structure. Okay. So you have this, let's see, oxygen in the middle, and then you have, let's see, in the background there, that. And then like that. So there's your tetrahedron. You got a hydrogen over here. These lines on the tetrahedron are not bonds. They're the geometric shape. Right? The bonds are still between here and here. That. And then the other corners, right? Here's a corner back here, and there's a corner up there, are occupied by the lone pairs. Right? So you have a regular tetrahedral shape for these groups. 4 groups means tetrahedron. And then if you want, that's the electronic geometry. The molecular geometry simply covers up the lone pairs and say, what do you got left? Well, what we have left is a bent molecule. That's why we write water like that. Okay. If you only have 3 groups, like boron trihydride, right, we drew the structure. It only has the 3 bonds with the hydrogens. 3 always means trigonal planar. That puts those bonding pairs as far apart from each other as possible. The equilateral triangle with hydrogen at each of the apexes. So that's 2 bonding groups 3 bonding groups, 4 bonding groups. Let's see. Oh, there are more. Okay, so when you use the VSEPR model, you have to draw the Lewis dot structure first. Then you count the number of lone pairs and bonding groups. Then you determine the geometry of the electronic structure based upon how many there are, right? Linear, tetrahedral, trigonal planar, and there are 2 more that I'll tell you about in a second. And then you find out what the molecular structure is by just covering up the lone pairs. Okay. So this one's linear. We drew that one before. It's only got 2 pairs, 2 bonding groups, and no lone pairs around the central atom. Okay. This one, pH3, is a trigonal pyramid. Okay, let me explain, because we sort of jumped right into that one. So pH3, the Lewis dot structure is going to be like that, correct? And 1, 2, 3, 4 groups means that it's a tetrahedron electronically. But it's got hydrogen in the back, and then hydrogen out here, hydrogen out here, and they form this trigonal base with a lone pair up here. And if you cover up the lone pair, there's your trigonal pyramid. Okay. Sulfur tetrafluoride. We haven't got to that one yet. Hold on a second. You know, let me see if I'm going to do it. I'm going to put this information in a slide, or if I need to draw it up. Well, I've got visible models, but I think it'll work better if I do it this way. So here in this column, I'm going to put the number of groups. Okay, so you can have one group is kind of stupid, because if you got one group, it's linear, no matter what. So we're just going to go to 2 groups, 3 groups, 4 groups, 5 groups, and 6 groups of electrons, either lone pairs or bonding. Then we have the electronic structure, geometry, excuse me, not electronic structure, electronic geometry. And then we cover up the lone pairs and we get the molecular geometry. Okay, if you have 2, it's going to be linear. If you cover up any lone pairs, maybe a lone pair on one side, a lone pair on the other, it's still going to be linear. There's no way around that. If you have 3, then the electronic is going to be trigonal planar. Right. If you have no lone pairs, they're all bonding groups, trigonal planar is geometry. If you have 1, then it's going to be bent. Right. I guess you could have 2. If you have 2, then it's just going to be linear. Okay. If you have 4, the electronic is tetrahedral. If you have 1 lone pair, then the molecular geometry will be trigonal pyramid. If you have 2 lone pairs, you're going to be bent. And if you have 3 lone pairs, you'll be linear. Give myself some more room here. If we have 5 groups, then you have a trigonal bipyramid. In other words, you have a central with 3 here, and then you have 1 up here and 1 down here. That makes 5. So a trigonal bipyramid is the electronic structure. Trigonal bipyramid. If you cover up one of those, let me draw that again. Here. Okay, so if you have one of these, where would you have the lone pair be to give you the best, the lowest energy? It wouldn't be up here at the apex. It's down here. So if you have one lone pair, it's going to be on that pair, that triangle. That means when you look at the structure, the molecular structure, then you would have kind of a, it's like this, there, and there. That's why we call it seesaw. So if you turn it on the side, it looks like a seesaw. But if you have 2 missing, now the best way to accommodate the lone pairs is to put those at the apexes. Now you have a trigonal planar with 2 lone pairs. 3 lone pairs, where would they go? The best way for 3 lone pairs is on the triangle. And that makes the molecule linear. Okay, one more. 6. The electronic structure for 6 is octahedral. Which is kind of like this one, only instead of a triangle, you have a square. Like that. So if you look at that geometry, it's got 8 sides. Okay, so if we're missing 1 on this one, where would it go? Well, it'd probably be missing, it'd probably be an electron pair there. And then what do you have? I'm not sure what you have there. I don't know. You have 2, they're going to go here like that. So you have square planar. If you have 3, they would probably go, I don't know. I'm not going to give you any of those anyway. So you don't have to worry about that. If I can't figure it out, I'm not going to give them to you. But now we look at angles. What are bond angles? Right? The bond angle here has to be, now we're talking about molecular geometry. So the bond angle with a linear is 1 here, 1 here, 1 in the middle, 180 degrees. That's the only bond angle it can be. If this is linear, bond angle, any linears are 180 degrees. The bent molecule would be, let's see, an equilateral triangle. The internal angles have to be 360. So 120, 120, 120. So the bent would have 120 degrees bond angle. Tetrahedron. The bond angles in a tetrahedron, if you've got 4 occupied positions in a tetrahedron, like carbon tetrafluoride, the bond angle is 109.5 degrees. You just have to memorize that. But if it's a trigonal pyramid, then what happens is you get this lone pair up here, and you have, what was it, phosphorus, and then you had hydrogen here, hydrogen here, hydrogen here. The bond angles here would start out at 109.5. But the thing about free or unbonded electrons is they're not confined by the neighbor. So they tend to balloon. And their repulsive effects tend to squash these down. So it'd be something less than 109.5, 107, 108, something like that. Same thing for the bent molecule, like water. It theoretically is 109.5, but it's got 2 lone pairs up there, so it's really squished, like 105 something. Okay, so trigonal pyramid, you got a triangle like that. So the bond angle between this central atom and these others here is 120 degrees, right, in the triangle. But here on that angle is 180. But the bond angle between this one and this one, any one of these on the triangle, is 90. So you got those 3 possibilities, 90, 120, 180. Octahedron. So if you got this square, and then you got something here like that, where the bond angles, well, here they're 90 degrees, right? 90 in the square, 180 here, or here to here is also 90. So those are the only possibilities, 90, 180 with octahedral. Okay, there you go. 107 degrees instead of 105.9, 109.5. Okay. This one's bent. That's ozone. We might have to look at, work some problems next time to get really into the weeds with some of these. Krypton, when we draw the electronic configuration of this one, I mean the electronic geometry, we find it's octahedral, but it's got 2 lone pairs. So they're up here like this, and all the fluorines are in square. So that's why this one is square planar. Molecule has polar bonds, will always be polar. False. Depends on the geometry. Let's see. I'm trying to look for anything that might. Okay, here we got pictures, right? But that you can look at these at your leisure. Right, a range of electron pairs. Actually, they keep saying pairs, but it could be groups because it could be a double bond, it could be a triple bond. Right, there's your trigonal bipyramidal, and there's your octahedral. They do a better job than I do when they draw it. And then this is the molecular structure if you have a tetrahedral and every position is occupied with an atom. But if there's a lone pair, then you get a trigonal pyramid. And if there are 2 lone pairs, you get a V shape. I call it bent. Some books call it angular. I just like bent. It sounds cooler. Okay, so here's a trigonal bipyramid. And the lone pair, if you only have 1 lone pair, it gives you that seesaw. If you have 2 lone pairs, T-shaped, and it could be T-shaped or it could be linear, I think. Oh, no, that's right. No, I think sometimes it should be trigonal planar because you put those lone pairs way up here, away from everybody. I think that now, the only thing that would trump my assumption is if they actually measured and they found this to be the real shape. And that's my guess. They probably did. On many occasions, it's T-shaped rather than linear. Excuse me, rather than trigonal plane. Okay. Let's see. These ions are going to have different geometric structures. PCl5, PCl4+, PCl6 minus, they will have different structures. You just have to draw the Lewis dot structures and then say, all right, what's left over after you accounted for the lone pairs? And that's what this slide does. Right, so there's PCl5. This is the structure. There are no lone pairs. So this is your geometric structure. It's trigonal bipyramid. If we go to PCl4 and draw the Lewis dot structure, right? And don't forget the charge when you're drawing the Lewis dot structures. If there's a charge, it needs to be expressed. This should be a tetrahedron, right? And there are no lone pairs to deal with. So the structure of this ion is a tetrahedron as opposed to a trigonal bipyramid. If we go the other way and add an electron, well, now we've got an electron charge, but we have 1, 2, 3, 4, 5. We have an octahedron, but there are no lone pairs. So the structure is octahedral also. Okay. You can form structures with inert gases, especially the bigger ones. They tend to be more amenable to forming compounds. Neon, some argons, never helium. And I've never seen any neon. Argon you can force. Krypton and xenon are pretty good at forming compounds. You just have to force them. So xenon tetrafluoride, what would be its structure? Right. So there we have xenon has 8, and fluorine has 7 each times 4 is 28. So 28 and 8 is 36. So we should have 36 here. Right? 2, 4, 6, 8. So 1, 2, 3, 4. 32 plus 34, 36. Did I miscount? 36. 8 plus 28. Yeah, I did miscount. 36. So we've accounted for all of them here. We've got 1, we've got 2, 4, 6, 8, 10, 12. We've got 12 around that xenon. But how many groups do we have? 1, 2, 3, 4, 5, 6. That means electronically, it's an octahedron. So there's our octahedron. Now we have to figure out where do these lone pairs go. I would put them at the apexes. That's as far as you can get away from each other and from these other bonding pairs. So this is one possibility. It leads to a seesaw. And this is the other possibility that leads to square planar. And if we look at the bonding angles, we find out that they're all 90 degrees. And that being the case, the square planar wins. We're getting close to the end. I hope so. I'm getting tired. And these may be polar bonds, but they're all equally spaced. And plus the lone pairs are out here canceling each other. So this molecule is nonpolar. No doubt.